Excellent. While Zach grabs caffeine, I'll start by kicking off and welcoming everyone to the Trustworthy ML seminar series. So, oh, pardon me. Here we go. So today, we started at the end, but let's start at the beginning. So today we're going to have a talk by Zach, but before I begin, I just want to welcome everyone and give you a little bit of context about what this series is. So the Trustworthy ML Initiative, if this is your first time at one of these talks, is really an initiative that came from a group of people talking about how do we bridge the gap between these different subfields of machine learning that are typically, until now, often treated in siloed ways. So how do we talk about interpretability, robustness, privacy, fairness? And one of our goals is to bring together a group of speakers that we think have interesting things to say about this topic. However, it's part of a wider initiative. So if you go to our website, we also have dedicated time to putting together a curated list of tutorials, courses, papers, and we really want this to be a platform for early career researchers as well as established researchers. So we have our Rising Star Spotlight talks, and you may have seen our Twitter highlight series. And if you have early career researchers that you think deserve to be profiled, feel free to send that to our Twitter highlight series, because what we want to do is really showcase some of the work being done. We want to encourage discussion and debate, and really ultimately our goal is to organize research symposiums and workshops where we can hear from many people in our community. And so with that, we have a fantastic kickoff to 2021. We're going to start with a talk by Zach. During the talk, feel free to add questions, to add comments. I'm happy to intermittently try to interrupt Zach and add the questions.
Yeah, please interrupt. Maximum interruption. That way when we run out of time at the end, I'll feel excused.
You'll feel satisfied, yeah.
Or
so I'll
to be more topical, I'll feel pardoned.
Excellent. I will aggregate questions and ask them sporadically. And then the talk itself would be about 45 minutes. And then I'll ask Zach some questions about his own journey and part of his wider research agenda. And then after that, we do have a participant-driven discussion. So we'll add another link, and whoever wants to continue the conversation will move over to that link. So I hope you'll join me there. But without further ado, I really want to make sure that we have adequate time for what I think will undoubtedly be a fantastic talk. So Zach will be talking about prediction data-driven decision-making in real-world environments. And Zach is a junior chair assistant professor of operations research and machine learning at Carnegie Mellon University and a visiting scientist at Amazon AI. His research spans core machine learning methods and their social impact, and addresses diverse application areas, including clinical medicine and natural language processing. Current research, which we'll likely hear about in the talk, includes robustness, breast cancer screening, healthcare applications, intersection of causal thinking, and the messy high-dimensional data that characterizes modern deep learning applications. So without further ado, over to you, Zach.
Okay, my AirPods are not working, so I think I might. That's
go
okay.
rogue.
Lo-fi today. Actually, sorry, let me just. I think I could at least give you better audio. How do I sound now? Do I sound much better? Cool. Wait a minute. No, I'm still. Now do I sound much better?
Unclear improvement, but go for it. I can hear you.
I'm on the podcast microphone. Carrie
so we
thinks I sound better.
Carrie says it sounds better. We have a vote from the audience. That's always a good sign.
Okay, cool. So I guess I should share my screen. Where to begin? Top left corner. All right, so thanks everyone. Thanks Sarah for a kind introduction that I'll invariably disappoint. Yeah, I'd like to speak about when I say predictions and decision making, and I apologize for dropping the conjunction when I sent the title. In real world environments, I guess you know, the focus of the talk, which will be a bit high level and a little bit philosophical, but delve into a few specific works that maybe elucidate some of these problems, is I think this sort of point of in real world environments sort of needs to be called out specifically because of how the way we formulate problems is in many ways sort of abstracted away from the sorts of environments or even the sorts of actual problems that we, believe we're addressing. And so I think it's precisely this, is sort of these sort of holes between the problems we think we're solving when we think about in a sort of problem-oriented manner, like problems in healthcare, problems in various public services, problems in various sort of customer, sort of very business applications. And then we look at how we formulate problems as machine learning problems. There's this tremendous gap that sort of divides them, and a wide set of desiderata that are just in no way actually accounted for. And I think the kinds of problems that arise when we start talking about trustworthy ML or any of the things that fall under that umbrella often are the result of precisely this sort of mismatch between the sort of technical lens that we have for approaching problems and what's actually demanded by the settings where we're sort of intruding. I guess I've already been introduced, so I don't need to say that much about myself, but obviously my work isn't done alone. Increasingly, as time grows larger, the fraction of credit that I deserve for anything that comes out of my lab or is associated with me is steadily decreasing. And I'm very fortunate to advise a bunch of amazing students at what we call the approximately correct machine intelligence lab. And broadly, the kinds of problems that animate us sort of have this character that we're interested in either, there's some amount of work on trying to, within the sandbox of just trying to get foundational understanding, but a lot of work at trying to broaden the scope of what we're viewing to the concerns of real world applications. So, we focus a lot on problems in healthcare, and, something that becomes immediately apparent in healthcare is that most of the things that matter aren't classification problems. There are exceptions, say like in pure recognition tasks, maybe in like, pathology. But for the most part, we care about doing better decision making. And this gap between what machine learning is doing, which is often classification, and the sort of claims that are made about, the role that AIs have in medicine, which is sort of assuming that we sort of have the ability to make decisions or reason, becomes really apparent, I think, when you sort of anchor yourself to thinking about life and death decisions in a way that maybe is easier to elide when you are looking at something like product recommendation. And the top right corner, the newest and fastest growing member of our lab, who you just met, is my puppy, Herbie. He's our post dog. So, just to remind ourselves of what we do, we talk about AI as having this role. I guess I used a copyrighted image, so you have these weird watermarks all over it. Apologies. I should find another picture of the Earth. You'd think if there's one thing you could get a picture of that wasn't copyrighted, it would be a picture of the Earth. Anyway, all right. So what we actually do is we sort of take for granted a setting in which just we have a set of inputs and a set of outputs. We often, as machine learning practitioners or researchers, don't concern ourselves with what input or targets are actually necessary to address the kind of real world problems we're addressing, or even whether the sort of area where we're intending to introduce automation is well formulated as a prediction problem at all. We just sort of say, assume the inputs, assume the outputs, and that's where our work begins. So these are things that are, so these purple arrows are introducing or conveying in this picture, is that there's something that's sort of taken as exogenous, and not just exogenous to the model, but exogenous to the entire process of research. And we sort of assume we're addressing a prediction task, and we assume that whatever data is sort of available to us is the relevant data for addressing the problem. I'd note, at a high level, this is very different from how, say, a natural scientist interacts with the world. Like, yes, they do plenty of function fitting, perhaps simpler function fitting, but what's, really sort of a distinguishing feature of the natural scientist versus the machine learning practitioner, the data scientist, is that they're asking questions about, what they're questioning, what are the questions worth asking in the first place, and what data are necessary, or at least, given our current theories, what data would be necessary to either clarify the applicability of the theory, or to falsify it, or to elucidate some new phenomena that the current theory gives us no way to describe at all. So we have this, weird divide between, we see our role as modeling usually in the sense of producing functions, classifiers that are fit in terms of, they achieve a low level of the risk as somehow defined. But then we have a sort of fanciful set of claims about what we're doing that involve, machine learning, being your next employer, or, revolutionizing healthcare, or making breakthroughs, and, doing all kinds of astounding things in scientific discovery that are, there's clearly a sort of conceptual gap between what we think we're doing when we talk about applications, and what we're actually doing when we go about sort of our business. I think, it becomes really apparent when you look at some specific problems. Recommender systems, what do we actually do? We predict clicks, or we predict purchases, or we predict ratings. These are all being done in a sort of supervised learning type fashion almost all the time. We might sometimes get a little bit clever, or adjust for propensity scores, for, somehow compensating for what system was in the loop before. But for the most part, we're formulating some kind of facile prediction task based on historical data, and trying to predict, some sort of somewhat arbitrarily designated target variable. And then we make claims about how we're making, prudent business decisions, or we're driving sales, or we're increasing engagement, or, we're intelligently curating personalized content. And so there's this gap between these things that, we're using these words that speak, not only to prediction, that, are the sorts of kind of very, human tasks we think we're addressing, but our actual machinery is not really directly taking any of those things on. So, this is sort of the pattern, right? We take some real world problem, we don't really know how to think of many parts of it, so we sort of project it onto, to commit that crime of using like machine learning metaphors for everything, or math metaphors for everything. We sort of project it onto the we have this framework that allows us to think about a very narrow set of problems, and we take the problems we're encountering, and we sort of project it onto the subspace of, things we know how to think about. We ignore everything that's sort of not sort of captured by the framework. So we go out and say, well, what are some covariates that are available? What are some targets that are available? Let's form a classifier, and then kind of think of what's some ad hoc way we could just throw this classifier into a business process, and try to build a product from it. And to be sure, I sound like I'm being very dismissive, or I am being very critical. But at the same time, I don't want to pretend that there exists something easy that we could do to fully automate these processes that isn't prediction. These are genuinely hard problems. So it's not that we don't have we're throwing machine learning these problems for the very reason that we don't in the first place have better ways to automate them. And at the same time, we maybe sometimes lack humility about the ways in which we're not really addressing the problems we claim. So I'm not necessarily saying we are ignoring some obvious thing we could be doing better, but rather that we're often confused about, what we're doing in the first place. And I guess, what is it? The first step to getting better is recognizing that you have a problem. Lending, I think, is another example. What we actually do is we just predict repayment based on some set of available covariates. Which covariates? Well, I don't know, whichever ones they gave to us. We don't really, whichever ones were captured in the system. So we don't ask, what are sort of the principles according to which we should make procedurally just lending decisions. We don't ask questions about even from a pure profit motivated standpoint, we don't usually ask questions about what actually is like a coherent set of incentives, such that if we make decisions there and then people react strategically, this will actually bring about sort of a healthy financial system. And I think, something that I'd point out here is that perhaps like the confusion of the machine learning community is most typified by this case, that when we deploy systems and then people start somehow behaving in a different way in reaction to the system that we deploy, we call this, we act as though these people are bad actors. We accuse them of gaming the system. But this is how decisions always operate in society. For example, when we make admissions decisions in, say, a program in computer science, and we say, oh, well, it's better if you've demonstrated aptitude in research, we don't accuse someone of gaming the system if they then go out and spend some amount of years in investing in their research career and their research knowledge and acquire some research aptitude and some artifacts to demonstrate it. We don't say that they're gaming the system. We say, well, we set up a good system of incentives. On the other hand, if you based, for example, lending decisions, so it's only when we start from the sort of, the stuff that sort of I think is very intuitive to us and we're able to deal with quite, like it doesn't confuse us in our daily lives. We don't go about our daily lives thinking that what you should do is sort of collect a data set and sort of make sort of arbitrary statistical predictions based upon whatever data is available, and then that you should sort of plug these into ad hoc rules, and that's how we should design policy. That's sort of never something that's natural to us. But once we start thinking with machine learning blinders on, we're sort of confused, and we start saying, well, if the system is accurate, what's the problem? Again, it's like presuming that accuracy is the measure with the accuracy on offline data. So we sort of like are able to, if not formally, at least informally, coherently address sort of dynamic settings in our everyday lives and think about how to craft policy. But once we start thinking from a machine learning standpoint, we get very confused. And we sort of say that we're creating smarter, objective, or fairer policies. And you have, these kind of goofy sorts of images. I just Googled for this last night and found this marketing mumbo jumbo from a turnkey lender about how together AI, machine learning, and deep nets are a boon to business awash in big data. So, we say all these things about we're making smarter, intelligent, whatever, but we're not actually even addressing the problem we came to be addressing at all. We're not addressing lending decisions. We're not even addressing the relevant sorts of data. We're not intelligently or in any way often accounting for the fact that we don't even actually see the outcomes for all the people for whom you made lending decisions, right? Because for all the people who you denied loans, you don't see repayment. So you only see the outcome associated with a subset of the population that's filtered by the machine learning model itself once you introduce it. Even the lending industry sort of talks about this. Machine learning papers in the area seldom do. It's called the reject inference problem, but the methods they have are at best confusing heuristics. In criminal justice, again, what do? We predict rearrest based on some available covariates. We ignore censoring, we annoy sample bias, we ignore considerations of procedural justice, right? So we never consider is some covariate in any way, is this a valid basis for making such a decision? So we look at things like how many siblings does someone have, or their occupation, forgetting in the very first place that policy about who to incarcerate and who not forms a set of incentives. And that when you use something as a basis for making a carceral decision, you're criminalizing that act. So it's like you're basically associating some legal consequence or import to having a particular occupation or having a certain number of siblings or any of these covariates that, it would sort of be absolutely bizarre, I think, if you weren't thinking through machine learning goggles that this should be the way the problem should be approached at all. But then, of course, when we talk about it, we sort of only speak in terms of machine learning metrics, right? So, or even to the extent that we think, more broadly, it's only just a little bit. So, we talk about improving efficiency. We make kind of vague claims that the system will be fairer or more just or more objective. Or when I say we, I mean, practitioners of ML applying this technology in practice. But there's a huge gap between what we're doing and what we're claiming to do. So, my sort of high-level characterization of problems that fall under trustworthy ML is, I've seen people starting to use the word trustworthy ML a lot as sort of maybe a broad umbrella term to characterize these problems related to bias and fairness, or reliability and robustness, or interpretability and explainability. And there's, a question of what do these problems all have in common? What I'd say, I think for the most part, they tend to have in common is that they're often speaking to desiderata that are sort of outside the sandbox. They're not really, they're in some sense not machine learning problems as traditionally defined. They're problems that arise that if you really ask someone what they're after, I think you start getting back to the point that the traditional machine learning objective was never someone's objective in the first place. So there might be some instances in which it turns out that, well, you can sort of endogenize this into the machine learning process. So you could say, well, yeah, you really just cared about the traditional machine learning objective. You just cared about it not necessarily as typically reported, like aggregate accuracy, but you cared about some subpopulation accuracy. And that if only you sort of refine the machine learning, you could basically carry on with the same kind of machinery. But I'd say a lot of these other issues, questions about reliability or robustness, reliability in the face of what? The answer is almost always something not, statistically represented in the data set. So it's basically violating the machine learning contract. We assume we're going to violate the machine learning contract, and we want to know if our model is going to still work nevertheless, which is something that, we're sort of either never dealing with or we're dealing with in a way that is sort of, maybe in a sort of like adversarial robustness sense of like, okay, we still assume the same underlying distribution, but just we introduce, the possibility of minute perturbations executed by an adversarial actor. So, like the high level kind of setup that I'm trying to convey here is one in which, we have a very narrow set of tools and a very narrow set of concerns that we're addressing. And then a sort of set of problems that arise because people, at least when they're not looking through machine learning goggles, are actually not so stupid, that, are sort of confounding us because they lie outside of the sandbox. They're not problems that are addressed by the machinery, right? So, I think we start winding up with these suitcase words, like fairness or bias, and we start applying them in a machine learning context, maybe not always actually knowing what we really mean by it in the machine learning context. And of course, we're adopting the sort of machine learning mindset of speaking generally about inputs and outputs and loss functions. So even being unclear about whether these are terms that, have meaning only in that framing. Like, can you just say, I have some inputs, I have some outputs, I have some whatever. Is there a bias or is there not? And sort of not, asking basic questions of identifiability. So I'm using the word identifiability a little bit loosely or gesturally, but I also am meaning it concretely in the statistical sense, in that, I think when we think with machine learning goggles on, we think only about, can I find the best predictor? And where the quality of a predictor is assessed by some metric that can be computed from the data that we have, from just, a random partition of data that we have. So that's sort of a question that is, for at least the sort of empirical ML world, nearly everyone in CV and NLP and in much of the sort of empirical deep learning world, but not necessarily the sort of theory or statistical world, that's sort of like the only problem that people have been addressing for the last 10 years, or with the exception of some work on, say, like reinforcement learning or whatever. But even there, you have this question of, everything is calculable. You have an environment, it spits out rewards. You can run your policy, you can get rewards. If you can run it for enough episodes, you can estimate what is the sort of expected reward. And so we're not used to asking about, the question of like, are the things that we care about, or the quantities that we're after, or things that are even identifiable from the data that we are given. So this is something that you have, becomes readily apparent if, say, you work on causal inference, which is that immediately you sort of see that a parameter of interest may or may not be identifiable from the data that you have, depending upon what assumptions you can make on it. And moreover, the different sets of assumptions might give you completely different answers and identify, completely different functionals that you should be trying to estimate, depending upon, which assumption is valid. And so, I think we're often leaping past this point of the fundamental question being, what data do we need, and what are we really after? And we sort of go straight towards the ML solutionist mindset, which is to sort of just start trying stuff. So, to elaborate on that, to give a little bit of a metaphor here, this high-level theme that I'm trying to hit on, it's, I don't know how many people remember the great children's story, Flatland, about, some two-dimensional creatures who live in, a space where everyone is a sort of two-dimensional object that can just hover around in the plane. And our protagonist is taken on it's been a while since I read it, but on some journey where they can go up into the higher dimensions and they see all these other, aspects of reality, the splendor of living in 3 dimensions that they didn't know before. And then afterwards, I believe they descend and sort of visit the other extreme, which is a world far less rich, and they go to Point Land. And in Point Land, you have a single being, this singular monarch who sits there, and he's basically just saying me, like everything is about me. And they start speaking to the monarch of Point Land, and the monarch of Point Land hears them, but is confused because he can only conceive of a world consisting of this point where he is the only being. And so the monarch of Point Land starts saying, oh, like what a wonder, my great mind, that I've even, developed this new voice. Like he thinks that everything that he is encountering is some kind of artifact of Point Land that is coming from him. It is, and I think we're doing a very similar thing in machine learning, which is we're sort of being confronted with all this information that sort of lies outside of the tools that we're sort of know how to use and have developed, but we're sort of just pretending that they are machine learning problems, business as usual, and going about our sort of standard practice of just throwing spaghetti at the wall and trying to calculate some automated metric and say what's the best method. I used to be on this website called Twitter before I was chased off by neo-Nazis. Maybe there I put it more succinctly in less than or equal to 280 characters. But right, it's like if we ignore all the parts of the problem that don't fit within our framework and just sort of keep only those that do, then yeah, surely we'll find that our tools are applicable, and we could publish papers. But unclear, whether or not we've actually addressed the problems or even made progress on the problems we sought out to tackle. And in general, this isn't just a problem of machine learning researchers. This is a recurring theme in science, right? So, not to invoke Kuhn like flippantly or incorrectly, but because I don't think what we're doing is exactly analogous to the natural sciences, and I don't think that what we possess is quite analogous to a paradigm in that sense. But I think there is some analogy that a recurring theme is that people have some sort of framework for addressing problems that they encounter, and the framework is maybe interesting and useful, and they're able to develop tools, and they're able to describe some things they find in the natural world, and they're able to use a certain kind of framework profitably. But eventually, you start running into problems that sort of challenge the power of the framework. And the first move is always just to pretend that these problems are actually not external to the framework, to just kind of contort the framework in a way, to pretend that these are problems expressible within it. So I think a good example here is if you read Yuta Pearl's Book of Why, he talks a lot about various ways that statisticians try to sort of contort probability to describe causality as though it were just something contained within probability versus sort of something that required the development of some fundamentally new concepts or primitives that you couldn't express within probability. And it turns out that is formalizing the idea of an intervention, or what Pearl likes to call the do operator.
Zach, we have some questions about the introduction of the framework. It might be a timely point to ask them. Otherwise, feel free to press on if you just want to do it at the end.
Sure. I'm trying to see where I can see. Should I look in QA or in chat?
I can ask them. So we have a question from Lee, who is asking, is the identifiability that you talk about similar to what Hannah Warich and Jen Wortman still call construct validity?
I think I'd have to read the passage in question to comment intelligently, perhaps.
And then there's a more broad question, which is perhaps getting to the heart. Is this inevitable? Kavaya asks, is this an ML specific restatement of the value alignment problem in AI? So are we just destined to have this problem of always having an underspecified function?
That is quite broad. How to answer? Look, I think if you put no limits on what you could be after, then sure, and quite often, you won't be able to solve it. But I think here, we have cases where, and what we'll get to a bit in the paper is, I think in the talk, there are cases where, there is there is information that matters. There maybe even are coherent ways of formulating a problem, but we're just completely ignoring them. Or we're asking the wrong question altogether. So, I think it might be too facile to just say okay, well, to exactly align with our sort of broader societal objectives is impossible. Therefore, we should confine ourselves to thinking of, sort of accept that there is inevitably some gap, and therefore we should confine ourselves to this sort of most hopelessly restricted set of machinery. I think is not the takeaway that I would encourage, but I mean, I think there's maybe a longer discussion to be had.
That life is futile. Well, one last question from Roseanne, which I actually suspect will lead into your next section, is building upon this. Roseanne is saying, so we can be aware of the gap, but is there anything that we can actually do for these metrics that we say we're not able to model? If the true object from Roseanne's word is unmodelable, which perhaps is a new word for the canon.
Unmodelable.
Yeah.
I think the meaning is clear, and the hyphens, are kind. I mean, so look, I think there's sort of a separate question of again, are you somehow fully dealing with all the, does there exist, when we say unmodelable, I think it's easy for that to become an excuse for doing nothing in some sense, right? Of oh, well, if we can't capture everything that we care about, then we should sort of, again, confine ourselves to sort of doing nothing at all. And I guess what I would sort of say is that like there are often like very clear aspects of a problem that do matter, that we don't in any way account for, even when they are sort of right in front of our face, you know, and that sort of, you know, I think this, you know, like this, you know what I'm saying? It's not this binary of like, either we are doing machine learning and kind of throwing out some arbitrary objective and just pretending that the data set in front of us is the only data we will ever see. And then, you know, sort of driving machinery in that kind of fashion, or we're doing, you know, it's either that or we have like solved everything in the world. I think, you know, there are questions, for example, you know, like in asking like the critical questions about what data we should be collecting in the first place, or very often I think we're applying predictive models where what we really care about is the effect of an intervention, where we actually do have some tools, you know, prospectively for trying to estimate, say, the effect of an intervention, and then sort of longitudinally for monitoring to see whether the intervention appears to have had the desired effect. And, you know, indeed, like, this is one of the areas, like there's a lot of gaps between machine learning sort of theory and like I think we often talk about like theory and practice, but by practice we don't really mean practice. We mean sort of like theory and then papers like, you know, published on benchmarks. But there are some ways that like the actual practitioners are savvy that sort of neither the machine learning theorists nor the sort of like empirical machine learning researcher are. Among other things, say if you take a company like Amazon or Google or whatever, they're sort of actually often kind of keenly aware, if nothing else from the profit-oriented like view, aware of the fact that they only have these sort of crude proxies for what they're hoping to automate, and as a result have, you know, these, now granted it's like clumsy and bumbling, but they have you know, these sort of pipelines and sort of monitoring protocols for, you know, even if it's from a standpoint of, you know, you swap out a recommender system for another one that had higher performance on ratings prediction or on, you know, purchase prediction or whatever it is. You know, a smart company isn't just going to say, okay, let's just replace the recommender system, do whatever. They're actually going to do a clinical trial. They're going to do, you know, an A/B test, or Amazon calls it a web lab, where you're going to run things. So, you know, I think like the people that are profit oriented have actually gotten sophisticated about these things in ways that they've been forced to by just the necessity of sort of running a business. And I think, you know, sort of the danger is that, you know, one is that, you know, that because academics aren't often focusing on those problems, at least with a kind of practical mindset, that the whole discipline of dealing with these things hasn't been in any way formalized, but sort of tends to live more in, you know, kind of the like organizational knowledge of companies, and rather, you know, it exists as sort of specialized to the things that, you know, profit-seeking companies care about. So like for checking out whether, you know, certain applications of machine learning actually achieve intended business objectives, they're actually sophisticated in ways for dealing with the dynamics of the real world that we are, you know, they are not, nor are we for addressing, you know, other sort of societal concerns. And so the danger is like, you know, it's sort of academics coming here saying we should care about fairness, we should care about this, we should care about that. But what we've thrown over the fence is a set of methodology that doesn't deal with it. We have a set of ad hoc practices that attempt to at least deal with dynamics as concerns profit. But we, the academics, who are the ones sort of saying you should also care about A, B, and C, are sort of unaware of what's required to deal with A, B, and C in any way, and we're not formalizing it. So I think there's a much longer conversation to be had, but I probably won't get anywhere near through my slides if I go too much further. Maybe I should continue a little bit and then we can pause some more. Sound good? All right, I will take the silence as agreement. Right. So, the prediction mindset is what we're, or maybe it just means I'm like somehow muted and don't realize it and nobody can hear me. Right. The prediction mindset, which is I think where most machine learning is still operating, as sort of, we fix some metric where the metric is just a function of, a classifier, a model, and a data set. And we try a bunch of stuff and then we return, the best stuff. And so one, we're sort of confined ourselves only to worlds where the metric is specified a priori, where again, speaking to this identifiability question, where we ignore maybe when all of the work is pushed onto the metric, or the question is, what is it? What is it that we should be doing? We don't take that on. We ignore the normative problem. We suppose that a metric would be somehow applicable. And so, we try to take whatever it is that bugs us and just sort of turn it into, whether it's adversarial robustness, whether it's sort of some overly facile fairness metric. And then again, we just try to say, okay, now our new metric is, some kind of objective that trades off accuracy and, some penalty. Now optimize that. And we immediately shift into our role is not to provide a coherent framework for determining what to do, but rather being, having it specified what to do in a way that is sort of easily sort of accessible. Our job is to just sort of again, go back into the machine learning sandbox and turn the crank on modeling. And, what I'd point out here, and I think is maybe the most sort of damning evidence that we've sort of failed on the fronts of, the work we're doing ostensibly for interpretability or for fairness or for even reliability in the wild, to different degrees, that despite the fact that we have thousands of papers every year coming out claiming in kind of vague ways to have put forth methods here, I don't think we actually have any coherent solutions that we can give the practitioner, or even a coherent mechanism for sort of mapping on some kind of description of their problem to any of the solutions that we have. And, I think for the most part, when we encounter the real problems, we don't really have anything to offer people. And so I think, we're sort of right in the sense that we are taking on real problems, but we're sort of wrong in the sense that we've gone about it in such a way that results in publication, but really hasn't, I think, addressed any of the underlying problems. I think for the person concerned with scientific discovery, I think they're finding more and more that if you, Lime or integrated gradients or class activation vectors, or whatever, really don't have interpretation, and that we're trying to explain the reasoning of models that don't actually have reasoning, and we're certifying models as fair without having any sense of what constitutes fairness in the domain. If anything, possibly having a sort of counterproductive effect of giving cloud cover to people to make claims of having achieved things that they haven't. So, we were in this crisis of we're concerned with a set of real problems, but unclear that we're making progress on them. And so I'd like to, kind of maybe go through a couple of areas where I've tried to, in a more concrete technical way, either elucidate some of these problems, or in some places to at least make, progress in some reasonably narrow way. So, to begin, we could talk about, and I'm using the overarching view for maybe my kind of angle on approaching problems in fairness as algorithmic fairness from a non-ideal perspective. And this is speaking to the distinction between the ideal and non-ideal approaches and political philosophy that we had a paper at AIES last year kind of articulating this. I guess the high level point I'd make here is that a lot of the problems we're talking about are not new to machine learning. They're sort of recurring problems that have happened. In the case of fairness, this has emerged over and over again, both among ethicists themselves in these debates among the ideal and non-ideal theorists, in the context of approaches in economics in the 70s and 80s to try to formalize ideas about equity, and now again in machine learning. And so if you're interested more in the sort of like broader philosophy on these problems, I have a paper with my postdoc, Sina Fazalpour, who made some nice connections there. This is the link. So, and what do we do in fair machine learning now? In most fair, machine learning, we have basically stuck with a machine learning sandbox of you are given a set of features. You don't really question what they are or whether they are the appropriate context for making a decision. You're given a target. You, again, don't really sort of understand what is the kind of decision is being made. What is it that individuals, we're talking about fairness, we're speaking about justice, right? Like broadly under the philosophy of justice, there's sort of a distinction. There's a number of like interesting binaries, and one of the binaries or one of the distinctions is between comparative and non-comparative rights. And so when we say fairness, I think we're just referring to the comparative variety. Those things were determining what, justice is concerned with giving onto people their due. Fairness is concerned with when does determining one's due require comparing how benefits and harms are allocated to sort of say one group of individuals versus another, versus non-comparative rights, right? Like we might have sort of non-comparative, like universal things that basically everyone is owed independent of what, anyone else is given. Like you can't say, oh, it's okay that I deny you, some kind of basic human right because I also denied it to someone else. So, okay, when we talk about fairness, we're talking about justice, just of a comparative variety. But, what's missing from nearly all of the actual work is a consideration of what precisely is the form of a problem, who are, where we can assess what is it precisely that individuals are due. And instead we just jump straight to this, ignore the context, here are the features, here are the targets. I'm going to say, let's just complement the situation by adding the notion of a sensitive feature and go right back, perturb the objective. So the objective now in some way depends upon the sensitive feature. So it's something like not just accuracy, but accuracy subject to some constraint, or accuracy as modified by some penalty, for accuracy defined according to whatever is your favorite risk function. But we go back to the machine learning crank, which is just let's churn out a model that, like here's the risk. We can assess it. We can assess it on holdout data. Let's turn the crank and churn out a model. And of course, the problems are you can propose any number of these metrics. All of the actual interesting work was in determining what is a coherent normative principle for deciding, what is actually in a given setting the right, what individuals are owed. And instead to just sort of say, well, this typical standard form of a paper is either to propose a new metric or take one off the shelf and just, propose a new algorithm to optimize it, or to look at a bunch of metrics and conclude, invariably that they're mutually irreconcilable. So you have this sort of, wide variety of impossibility theorems to choose from. And the problem, of course, is that for most of these metrics, if groups of individuals are statistically identical, this is actually easy. All you have to do is be blind. Otherwise, you just find that the metrics are all reconcilable. And of course, like the cynic's view of this, or the tendency of the cynic is to take away from this that, oh, fairness was impossible in the first place. But I think what it really elucidates is just that all of the work in the first place was in determining what is appropriate in this context. And that actually making minor adaptations to the machine learning machinery to sort of suit a particular metric was never actually the societal problem in the first place. Moreover, the metrics that people are proposing are often, suffer this issue that they are not even corresponding to the legal or philosophical notions that authors claim motivate them. And I'll kind of highlight that in a second. So again, just the highlight, and perhaps this being, as I don't have time to get too deep into it, but so maybe I'll just proceed a little bit here. So here's an example of two metrics and like how things go wrong. And this is from a paper about does mitigating machine learning's impact disparity require treatment disparity, with Alex Choltachova and Julian McCauley at NeurIPS 2018. There's a class of papers that say a model that you deploy should not look at the sensitive feature, be it, race or gender or whatever. And this is loosely motivated by a sort of misinterpretation or an overly reductive interpretation of Title VII of the Civil Rights Act from disparate treatment doctrine. And they also say, well, you should have identical fractions of individuals get some, or some other metric should be concerning the outcomes. Outcomes here being interpreted as like the assignment of a classifier. Again, that's a huge leap, assuming that the making this leap from the output of a classifier to the actual decision that is taken. I think, again, speaking to that confusion about the difference between predictions and decisions. And so they say, okay, the outputs should, in some sense, the outcome should be identical, and you're going to assess this by incorporating a sensitive feature into your computation of the loss, but they shouldn't be used as inputs to the model. So again, these two sort of conditions are loosely inspired by United States anti-discrimination law, specifically the Civil Rights Act of 1964, which has introduced two doctrines. One is about concerns disparate treatment. So again, this idea of like sort of grabbing things we think we're addressing and sort of projecting them onto the subspace of machine learning concepts. Disparate treatment concerns intentional discrimination, which includes decisions that are explicitly based on protected characteristic, but also includes intentional discrimination via proxy variables. Again, here we have lots of proxy variables. All of our covariates are associated with our sensitive attribute in general. And the part that people don't know how to wrap their heads around is what precisely do we mean by intentional? And so what ends up happening in ML literature is they say, let's just ignore that. We don't know what it means to, let's just say disparate treatment means don't use a protected characteristic. So people adopt this and they start using legal doctrine to describe the sort of reductive, formal notion of just blindness, like don't use a sensitive feature as input to the model. Of course, by ignoring this question of intentional, they license all kinds of models that would potentially throw weight on features that serve no other purpose but to be proxy variables, because they've sort of forgotten about this sort of what the doctrine actually means. In fact, I'd go as far as to say that I think many or most people using these terms in machine learning papers haven't even bothered to read the several pages that constitute Title VII of the Civil Rights Act. And then you have disparate impact, which is, again, a very complicated legal doctrine that says, facially neutral practices that might nevertheless have an unjustified adverse impact on members of a protected class. So it's basically the idea is to say, even if you don't look at, you don't incorporate race, you don't incorporate gender into a decision, you can nevertheless, based on other features, even if you don't appear to be using the feature, based by using correlated features as inputs to some kind of decision-making process, you might nevertheless have some kind of disparity in outcomes. But the law isn't just concerned with disparity of outcomes; it's concerned with this idea of an unjustified adverse impact. And so, of course, we're not quite sure what constitutes justification. When is it okay? What are precisely the sorts of disparities that we have an obligation to remediate? And so when we ignore that, we just start talking about disparities. We're unable, for example, to distinguish between settings in which one group has a disparity over another because of some historical process of discrimination, and another group, for example, like outperforming immigrant groups, are maybe overrepresented. There's some disparity in acceptance rates of, say, like East Asian Americans over white Americans, but not because they've benefited from some historical, pro-Asian discrimination. And so these are salient differences that make a difference. They make a difference to the law, but they're sort of ignored when you throw away this question of whether or not the disparity is justified or what constitutes justice in the first place. And so we analyze these algorithms that are being used that are being justified on the basis of, say, hey, they don't look at the feature and they satisfy some output parity. And we find something kind of peculiar, which is that basically, well, the ideal way, like if your goal is to maximize accuracy subject to, minimizing the outcome disparity, the optimal thing to do is just make the best predictions you can and set some thresholds. This is like sort of simple theoretical result that we can get. So this now is something that the papers proposing these algorithms ignore. They claim to sort of be impermissible because it would constitute disparate treatment. But actually, this isn't what disparate treatment says. In fact, disparate treatment is a sort of complicated legal doctrine as it's been interpreted, and it's actually considered in many contexts. And there was an interesting paper by, I think, Deborah Hellman recently that made this argument, from a greater position of legal authority than I possess, that actually using race, for example, or gender as part of a decision, not in a way that creates discrimination, but that is consciously done to mitigate discrimination or to increase parity, is not necessarily impermissible by the law. So this is not necessarily what is actually prohibited by disparate treatment doctrine. Moreover, if you have a classifier where you can sort of arbitrarily accurately recover some sensitive feature given the non-sensitive traits, then what these models are going to do is actually going to be indistinguishable. They're going to exactly recover the thresholding policy. So essentially, we proposed a class of algorithms thinking that we're addressing some social problem where we believe that the social problem precludes the explicit use of some feature. But actually, what we recover is a model that basically explicitly uses the feature exactly as the thresholding policy would. So it's sort of like ML being used naively to just sort of launder doing exactly something that the practitioners somehow think is impermissible. And where things get really weird is in the actual real world, what ends up happening is that in most data sets you can infer with some degree of fidelity, but not perfectly, someone's sensitive feature. So you can infer their gender or their race based on their other covariates to some degree of accuracy that is far better than random, but far from 100% accuracy. And when you actually deploy these models in a setting, you get all kinds of bizarre side effects. And so I guess I've ran way out of time, so I don't get to talk about my work on domain adaptation and robust and standard distribution shift, but I hope at least I can maybe complete this portion and then take a couple more.
Absolutely. We'll keep running and you can complete the slides. I know some people may have to go, but for those of you who can stay, we're happy, and we have plenty of questions afterwards, so feel free to take your time, Zach.
Okay, cool. And let me just make sure that my next meeting knows that I'm running late too. This pause can be fixed in post-production, right?
Yes, YouTube Live may have that feature, but you may be in a little bit of trouble. But this probably adds to the authentic nature of live presentations.
Distracting everyone with my beautiful puppy.
Excellent strategy.
Okay. So I want to give an example of where this kind of like naive casting of to make things more concrete, where this naive casting of a serious social problem as a machine learning problem, and then the sort of turning of the crank leads to methods that could be really dangerous if applied in practice. And keep in mind, right, we have a very simple policy, which is what we could do is either not use machine learning. That's always an option. We can always have hey, come on, Herbie. A proper admissions process in which there's human review, or we could, apply our machine learning, but say we just want to increase, we want to overcome the disparities, say gender disparities in CS programs by explicitly saying we want to admit more women and we want to, we're willing to admit less men, which I think is a totally reasonable thing to do. But instead, people sort of contrive this way of turning this into a machine learning problem and say this thing's impermissible and this thing's impermissible. These are our constraints. Let's turn the crank and maximize, utility subject to, the constraints or the penalties as they may be. And so here's what happens. We have a data set consisting of 9,000 students applying to be admitted to a master's program in a large US university over an 11-year period. The labels, as you would imagine someone would naively construct such a system, or just the admissions decisions that were provided by a faculty admissions committee, for those same students historically. So this is whatever decision was made for them. Now, our protected attribute of interest is going to be gender. And we also have access to country of origin, interest area, GRE score, some other related covariates. And just to make sure that the data set sort of is well motivated for our purposes, this is sort of a semi-synthetic example. We flip 25% of historical admitted women's decisions from positive to negative. So this is just, in case you don't believe that in the original data there was any bias, we're saying that now, even many of the women that, would have been admitted by our hopefully progressive admissions committee, that they actually, had rejected a considerable number of them. So now you could apply this model that is sort of optimized in this way to, and so what would be the standard thing to do? The standard ML thing is, let's just try to train a model unconstrained, give it all the features, it's trained to predict will someone be admitted or not. And then we're going to set some kind of threshold, and the top fraction of people, anyone whose score exceeds some amount, we're going to accept them, and the people below it, we're going to reject them. That would be sort of like the standard naive way of applying machine learning to make a decision. We've picked our proxy variable, which is historical decisions. We've trained a predictive model, and now we're sort of treating that score as the basis for making a decision, or higher is better, lower is worse. So you could see happens now is that you can now say, instead of using so if you see like all the points here, initially you're seeing the y-axis is just, if you just train the normal model, where is, what was the probability of admit given their covariates? And now what we can also do is we could train a model given only the non-gender covariates and train it to try to infer gender. So in some sense, like, how likely does the model, think, so to speak, that an individual is male versus female? So we get this scatter here. What we've plotted is the probability that the individual, according to the best predictor in the class, is female given their non-protected covariates, and the probability that they're admitted given all their covariates. And we could look and say, what would have happened historically if you just sort of did the naive ML thing, is you would have just looked at probability of admit given the covariate, set a threshold, which is this dotted black line. Everyone above gets admitted, everyone below gets rejected. If instead you apply off the shelf one of these machine learning models that's sort of trying to solve, the ML constraints, causes a machine learning problem, what you find is you get this different predictor, which is, okay, it's still close-ish to the threshold, but what we've colored is all the individuals who get their decisions flipped versus if you did the naive thing. And something that you'll observe is, the blue arrows are women, the yellow arrows are men, and the upward-facing arrows are individuals who otherwise would have been rejected but have their decisions flipped to positive, and down is, would have been accepted but flipped to negative. And what you see is that by switching to this ML approach, you end up, benefiting some women, but also hurting a few women. You benefit more than you hurt, but there's individuals on both sides that are advantaged and disadvantaged, even among the group that you aim to protect. Among males, there are a bunch of males who have their decision. Basically, males who the model thinks are unlikely to be female. So males who the model thinks are likely to be male and were just above the threshold are downgraded. Males who the model thinks were likely to be female actually benefit from, the algorithm. So again, this is likely to be female based on their non-protected covariates. So what ends up happening here, which is weird, is you could dive deeper and say, so we've told the model it's not allowed to use gender as a trait, but we've told it that it has to satisfy gender parity in the outcomes. So how is the model able to do that? And the only answer is actually the model has to depend explicitly on features that are sort of correlated with gender. So we've sort of we think that we're not using this feature directly to set thresholds because, disparate treatment doctrine prohibits it. But actually what you're doing instead is precisely something that's also prohibited, if you're going to take that strict interpretation of disparate treatment, which is you're relying on these proxies. For example, if hair length were a feature, then, it would be an important feature in the model. So, I might benefit, but, most men, quarantine has changed, the whole landscape. So we dive deeper here and we look to see sort of what is driving these effects. And it turns out that the feature that the sort of proxy variable that the model picks up on for being able to satisfy the outcome parity constraint is precisely interest area. And this is especially dangerous because what it ends up doing is that within computer science, you have many different subfields. And some of these subfields already have a reasonably good progress towards gender parity, and others are extremely skewed. And what this basically says is that you go and you look and you say, so like among women, some women benefit from the introduction of this policy, some are harmed by it. So who is helped and who is harmed? And the answer turns out to be that the ones that are helped are the ones who, by and large, want to go into subfields that already have good gender parity. Because, say they want to go into a field that has good gender parity, then the model thinks because of that, because more women wanted to go in those fields historically, they have more women were admitted to them historically, that, if you want to go into one of those subfields, you're more likely to be a woman and therefore should benefit from it. However, the women that want to go into the fields that most need to be diversified, the fields that have the greatest disparity, actually are hurt by this algorithm. And so, I hope this gives some kind of sense of that, if you sort of just cast things naively as a machine learning problem, and you sort of just naively take these sort of societal desiderata and just sort of cast them as constraints and then start turning the cranks of risk minimization, you can come up with something that, via these, sort of, aggregate metrics that you're looking at look sensible, but actually it's completely incoherent as a policy for promoting the kinds of outcomes that we care about. Perhaps is, has a deleterious effect versus a sort of benefit towards societal aims that we have. So I had, plenty more slides and had hoped to speak about ways that maybe we are naively approaching questions of robustness, and some ways we're beginning to inch towards them. But I hope, at the very least, maybe our leisurely talk gave us the ability to not rush to front matter. And I will plan next time I try to give this talk to ask for 2 hours. Anyway, thank you, and I'll stop now.
We'll have to invite you back for part 2. Thanks for the talk, Zach. We do have some questions that have been coming in throughout the talk. So I think one of the most interesting ones to start with is actually from Sebastian, who's asking, is this dismal track record with respect to objectives like fairness, robustness, is it due to a lack of consensus on the informal definition of these concepts? So perhaps what Sebastian is saying is it's not so much that they're unspecifiable, it's perhaps that the discourse in these subfields is fairly young. What would you say to that?
Well, I mean, I think there's sort of 2 sides. On one hand, these are genuinely hard problems. But on the other side, I don't think most of the work is even on the track to make progress on them. So, for example, it's like to kind of go towards like interpretability or something. If your goal is to establish some kind of coherent paradigm for like scientific discovery or discovering concepts from data, and your way of going about it is to this kind of like, well, what if we just look at the gradient? What if we take the gradient and we turn it upside down? What if we take the gradient and we spin it in a circle, whatever? Like, I don't think that work is even moving in the direction of its stated aims. And so I think on one hand, yes, like, when you encounter areas of like conceptual ambiguity or where there is conceptual work to be done, progress, can be slow, or, there are some fundamental obstacles, but I would point to that, like, it's not that there's no action on those fronts, but, that there's this weird discrepancy that, I think it's sort of like, I think in some ways it almost like reminds me of like the state of like, maybe, I don't know if this is a great analogy or not, but maybe like the state of privacy research. Some number of years ago, it's not to say that differential privacy captures everything that we sort of informally care about as concerns privacy and information systems, but that like this was the innovation to allow people to make progress was to think really, really rigorously about, like there is like to actually do the conceptual work of coming up with sort of coherent problem formulations that actually do capture some aspect of the problem of interest. So, I mean, something that we didn't talk about, but that I have slides for is, in domain adaptation, for example, or in this, robustness, we have a whole literature of people saying that the models depend on spurious patterns, and they capture the biases, and they capture the superficial this and the textures and this and whatever, without ever really, or like in NLP, this whole literature on what they call artifacts. It's all the model's picking up on the artifacts. But, so you have thousands of papers that sort of are proceeding in a way where they're sort of like doomed at the outset, because it's never made clear what is an artifact, or is even distinguishing the artifact from the thing that you had hoped you would learn, something that's identifiable from the data alone versus what set of assumptions. So I'd say that there's this, it's not to say that if, how do I put it? It's not to say that like if everyone was working on the conceptual work, we'd be light years ahead of where we are now. I don't know if we would be, but it is also to say that I think, are actually doing something counterproductive when we're sort of faking it, And so I think when we have these thousands of papers that are not addressing the problems they purport to, and are sort of making these sort of quasi-scientific claims that make it sound as though they have, you wind up in this world where you sort of have to do more work. Like I find that I very often, like the very first step of working with a lot of students is having to
unteach.
Yeah, like to deprogram students from having a kind of gullible relationship to the literature. It's like, oh, but I read this paper and it said that this thing is whatever, and it's like you have to say, well, do you believe this claim? Like, does it even mean anything at all? Are any of the terms that are part of this ostensibly formal claim actually defined? And the answer is often like that you sort of need to, I mean, I see a counter argument there of like, look, in some sense, like everyone needs to learn to think critically. And you never want people to have a completely gullible relationship with the literature, even if the literature is very high quality. But I think the danger is when you get to a point where, you almost, you can trust almost nothing that you read. I think this creates like a very dangerous kind of climate for doing research. Where it's almost like someone needs to go back and rewrite the literature in order so that people have something to build on top of.
So I do have a question that I would like you to answer, because it's from Lee, and Lee is, I guess, prodding you to think of not just the grumpy examples, but some positive. So Lee asks, when do you think that subspace projection reduction to supervised learning works well? This is from early in your talk. And when does it not? I think that you covered when it doesn't quite well, but can you think of any examples where reducing it to these basic metrics is sensible? And then after that, I'm going to open up. We have this reduced social hour, but I'm going to open up for the rest of this half hour to hear from anyone who wants to reflect on what was discussed. So, but first, I would love to hear your response to Lee's question.
I think it's actually quite often, and I think it's almost like a strange miracle that the technology, like, I mean, I'll give you an example would be search. So search is sort of like, like, you could think about search forever and never run out of things that are problematic about, and ways in which, like, this sort of click optimization, determinations of like relevance are sort of, what's not captured by them, all the sort of problematic content that is surfaced, all the things that they're unable to distinguish between that you would like them to be. And at the same time, like, we would have no ability to function on the internet absent the search technology that we have, which is largely driven by, things that are kind of it's obviously modern search systems are quite complex and they're sort of a hodgepodge of different technologies, but largely like fit into this umbrella of, brute optimization of these metrics that like you couldn't access the internet without it. And the fraction of time that you actually do find what you want, or not even just find what you want, find things that are truly useful is really high. And I know there's all kinds of other things that are happening, and obviously personalized search, there's content that sort of just gets upweighted for everything, not because it's relevant, but because it's just people can't help themselves and they click on it, and the model doesn't know that the question has some semantic meaning, and you wind up having to have all kinds of crazy ad hoc guardrails, just to suppress the amount of, whether it's like, pornographic content or whatever that otherwise would show up in an organic search, sort of left to its own devices. But like the very fact that we have technology that works at all, that allows us to navigate the internet, is kind of a miracle. I mean, I think recommendation systems are a little bit like that too. Like, I think there are some companies doing a better job than others. Like, I find that I'm more impressed by whatever Spotify is doing than by whatever YouTube is doing. But the fact that, like, these systems are ultimately left to, like, okay, Spotify might do a very good job of getting at least in the weeds of music and terms of like music information retrieval type content, and getting, song attributes that inform their recommender, and combining this in some kind of reasonably intelligent way with collaborative filtering type approaches. But like at the end of the day, they're doing some kind of like passive signal based optimization. And yet, nevertheless, I'm surprised how often I do discover music that, I otherwise might not have through Spotify. So it's like, the reason why we're using these clumsy tools here is, I think, because they're in the very first place, like, hard problems where we don't have an alternative. But, like, clearly we have a lot of technology that is, useful or indispensable. However, kind of dangerous and broken it could also be.
Yeah, that's really interesting. We do have another question in the thread. However, I also want to suggest, since our discussion time has been a little compressed today, if anyone would like to speak, just raise your hand or ask a Q&A, and then we'll unmute you so you can state like a reaction to the talk. But in the meantime, while people are raising their hands, here's a question from Vijayant, and he's asking, does the lack of identifiability in model design relate more to the inherent flawed belief in ML that more data can address lack of principle systems thinking? So is this lack of attention related to our belief to just throw more data at the problem?
Can you restate the question again? Sorry, I was slightly distracted by a dog urinating. He's been, engaged in a reinforcement learning exercise that is progressing steadily but slowly.
I wish you luck with that. So the question is really saying, is our lack of attention to identifiability, what you call identifiability, is it related to how we seem to not spend much time thinking about specification or system design in general, because we are focused on just throwing more data at the problem, so to speak?
Well, I think it's, I think it's an artifact of a couple of things. One, I think it's our tendency to try to come up with sort of blanket solutions for problems that look similar in terms of their like shape as prediction problems. And so I think when we now encounter some questions about like societal concerns, we just assume that like, okay, this is how you deal with fairness and classification. Like we're used to categorizing, we have an ontology of categorizing problems that is based on like the shape of the inputs, the shape of the outputs. And I think we also have a culture of convenience. You know, I think like for like economists or even like, you know, statisticians, I think they kind of laugh at, or think we're engaged in some kind of strange clownish enterprise when they see like, oh, you know, somebody graduated from PhD and they have 74 papers and they're whatever. It's like how is this a paper? Like what? And sort of, you know, there is this problem that like when you're, if your sort of culture is that you, like a paper is something that you do in 2 weeks and spit it out, or a month, or as, you know, the average pace, you know, obviously, you know, if products running concurrently, but you know what I mean? If you stack it up, if that's what it constitutes, that doesn't leave room for the kind of situated engagement that, that I think actually thinking about a problem. So I think there's a few things. One is like our tendency to just try to come up with general solutions and to sort of ignore the ways in which these different problems that, you know, might look similar from a prediction standpoint are actually very different in terms of the social problem that, you know, they represent. And the other is just our sort of maybe addiction to convenience, that like we only work with the data that is already available for us, that we only work with those aspects of the specification problem that are, you know, come pre-packaged with the data set. And we sort of almost don't see that as like under our purview. I mean, just in general, that sort of focus, it can lead us to just all sorts of goofy conclusions in general. And here's one that I've been thinking a little bit about, is we talk about medical diagnosis as like a important application of machine learning often. And people, you know, including myself, have papers all the time where you sort of look at a set of features that include something like some kind of structured formulation of whatever is available in the electronic health records. This is, you know, whether it's like these are all the vital signs that have been recorded, the blood tests that have been recorded, the codes that have been recorded, whatever. And then we try to predict like what is the diagnosis associated with this patient. And the bizarre thing about that is like, we call this diagnosis when we're like machine, we're saying, oh, we're doing something like what the doctor does. But actually, this was never the hard part of making a diagnosis as a doctor. The hard part was never like assume that all the tests have been run and all the results are in. Can you accurately, you know, draw the statistical inference of like, now given all that information? Like the hard part of diagnosis is always like you start off with a patient with no data associated with them, and you have to decide what tests to run, and you have to decide whether to observe them, and you have to decide which patients should come for more frequent visits and which shouldn't. So it was never like given all the data, make the decision. The hard part of the problem was deciding what to observe in the first place. And there's actually another line of research that I'm working on a lot, is this question of like, you know, like the thing that we take for granted is what are the covariates? But actually, if you were in a situation where, you know, there's a cost to observation, and you're in more a situation like what the doctor is in, which is that you want to learn something about how the world works, but you can't give every test to every patient. You know?
Yeah. That's really interesting. I want to perhaps pause here because we're in our final 3 minutes. I did want to quickly plug for next Trustworthy ML series. We'll have another talk from Carnegie Mellon where Stephen Wu will be talking. And the last question I wanted to ask you, perhaps as a way to wrap up, is what direction of research do you find promising right now? What are you excited about?
Me?
Yes, I mean, I do understand it may be difficult to refrain from being grumpy, but what questions are underserved and merit further work?
I think there's a lot of things to be. I mean, I know this is our, I guess others are not privy to our long running, teasing, but, I actually think that, there's a Silicon Valley maker culture where if you're critical of something, it's like you're a builder or you're a hater or something. And I actually think that, science doesn't sort of, my kind of take on what constitutes creativity is that creativity is just like the highest form of criticism or something. It's that is, if you start off, you don't work on things and you don't have anything to contribute in spaces where everything makes sense. And so I think the first step to a positive contribution for me is the identification of some kind of melody. We're doing it all wrong. To me, this is when I'm most excited that I have something to offer, is when I'm really convinced it's like everything smells wrong. Then there's some, so I think you find these areas in the literature where this discussion of the spurious signals in text, or it's depending on the wrong reason. What does that actually mean? It's so clearly wrong. It's so clearly incoherently expressed in the papers that you start thinking there has to be. It's not that it's just that it's wrong. It's not. These people aren't just speaking in tongues. They're clearly speaking to something that seems right, that it's a problem, and wrong in how it's articulated. And to me, that's always then a sign that there's something better to be done. The first step is to be completely clear about what is wrong or what is missing. And so, for example, on that side, when it comes to the spurious patterns, the text, one thing I've been excited about, and I don't know if he's still on the call, but he was joined earlier. He's still here. So my student Divyansh Kaushik, we've been working a lot on these questions of, people are sort of part of what seems wrong to people is that it seems the model depends on something, it is sensitive to something that is not the difference that makes the difference. It is sensitive to the background when the only thing that really determines which object category it belongs to is what's in the foreground, or it's sensitive to you train a classifier on movie reviews to try to predict sentiment. It's sensitive to mentions of genre. So if you flip the genre of the movie from horror to romance, the assessment of the positiveness of the review becomes more positive, even though you haven't said anything that's semantically positive. And so, one thing I've been excited about is trying to look at some of these problems through, if not using the mathematical machinery, using the intuition and maybe philosophy of causal thinking. So there's sort of maybe two ways to think about this. One is that there are certain utterances that actually cause the label to be applicable. There are other utterances that are maybe predictive, but not directly causal. So the reason why that would emerge from a causal perspective is this then becomes well articulated, is that there's some kind of common cause. So the budget of the movie, there's some kind of common cause that the budget tends to influence the quality of the movie and also the choice of what genre to make. But conditioned on the actual underlying quality of the movie, the genre really has no impact on or I should say it. Things get a little bit weird because we're talking about the actual quality and the implied quality of the, from the review. But I guess the point is to say, you have these features that there is some common cause that links, certain attributes that are discussed in the review, but they are not all the things that directly cause the sentiment to be applicable. And then the question is, well, can you actually disambiguate these things from looking at the text alone? And the sort of hypothesis, the natural hypothesis, I think, is that they're not. In the same way that, if you don't understand these background factors that influence how what's predictive of what, that you can't just, just look at the data set and just propose a new machine learning model that in general is only sensitive to the things that cause the label to be applicable versus not. And so in our case, one direction that we've been really excited about is using annotators in creative ways. So rather than just having an annotator there to give us a label and we say, now we have a larger label data set, let's learn this, it's to use the annotator to try to, in some sense, disambiguate what actually causes the label to be applicable versus not. And so something that I had in a slide I couldn't present is we have an interesting interface where basically instead of having the annotator and say, here's a document, is it positive or negative? We sort of have a data set that's already labeled. And we say, here's a document, the sentiment is positive. We want you to edit the document in such a way that, doesn't intervene upon factors in the review that are sort of not semantically relevant to the sentiment. We only edit it in ways that are necessary to make it sort of conform to the counterfactual sentiment of negative. So you find something interesting. It's like if you train a model on reviews, you find that things like the word horror is predictive of negative sentiment, romance of positive sentiment. But if you actually look at the data that has been manipulated by the reviewers to agree with these counterfactual labels and you train a model, you still find that words like fantastic and terrific are positive and words like terrible and awful are negative. But the role of genre flips because the annotator has revealed something to us by their choice of what to intervene on versus not to intervene on. So by the fact that they don't intervene on genre brings up about a case where now in the revised data, all those horror reviews that were negative are now positive reviews, but they still contain the word horror because the annotator has sort of communicated to us by not changing that word that this is not something that needs to flip in order to flip the applicability of the sentiment label. And so by now training on this augmented data, we're able to produce classifiers that seem to depend, neither on neither on horror in a positive way nor on a negative way when you combine the original and the counterfactually revised data. So this idea of like thinking what else can, what is the sort of, even in these like messy data sets like natural language, what are the ways that we can use humans in the loop to try to elicit in some sense like structural knowledge? So that's one thing I'm super excited about. In general, I'm super excited about just broadly is outer loop concerns. Like what are the sets of invariances that we could postulate where we could then actually develop coherent algorithms that'll be in some sense provably robust on data that doesn't respect this invariance. If you assume nothing, then nothing is possible a priori, and that's easy to show. And also, those concerns, like I said before, is questions about like where does data come from, and if you see the role of the learner not as to be given a data set, learn something, but they're interacting with the world, and each turn they have to choose which variables to observe, and that's they have to make the choice. So these problems, obviously, some of these things are have a much more of a HCI aspect to them. Some have much more of a kind of like a learning theoretic aspect. But I think broadly the unifying theme of what I'm interested in is getting outside the sandbox and addressing these sort of outer loop concerns.
Yeah, that's a fantastic way to wrap it up. Honestly, thank you so much, Zach. I really enjoyed both the talk, the tangents, the questions. So really appreciate it and making the time.
Yeah, thanks for having me. And sorry to be such a nightmare to get a hold of by email. I assure you that I'm always bad about email, and
not at all.
Not anywhere personal, and I hope to become a better emailer in 2021.
No, absolutely. New Year's resolutions. That's what we're about. Thank you again. Thank you to everyone who attended and for all the questions. We didn't get to all of them, but we did get to many, and it was really fun having you, Zach.
Great. Thanks, Sarah. Thanks for having me, and thanks, Hema and Chavi and everyone who's organized. And